All right. So we spent a lot of time talking about curves, which is great because curves are way easier than everything else. So you can state lots of nice theorems about them. But I feel like we should say like a little bit of something about surfaces. Don't have a ton of time for them. Um, so surfaces, though, of course, for me, just means two-dimensional varieties. Usually smooth. Um, and what do we want to say about these? This is an interesting question. Curves, there's this sort of beautiful, incredibly simple classification by just genus. And then you can kind of think about these guys by genus and families. And surfaces are way weirder. So the first kind of illustration is for curves, there's this beautiful theorem um, that, let me get this right, not say this wrong. Um, a birational map between smooth curves is an isomorphism. Between smooth projective curves actually has to be an isomorphism. And even if I didn't say projective, it would have to be an inclusion. Or sort of the inclusion of open subsets, which you can sort of projective curves is an isomorphism. And this has to do with this curve into projective extension theorem, that if I have a map from a curve into a projective variety, I can actually extend it over any point that I removed. But that's something really special about curves. It sort of has to do with the fact that, that the local ring on the curve is a DVR, which apparently is, the one thing you should learn from this course, according to Robert. It's not the Hauptidealsatz. I mean, it's not something you can. I mean, there is a commutative algebra version of this fact, but somehow, if you say something that involves projective varieties, it's kind of hard, to state that as a commutative algebra thing. So, right, the key thing here is on a curve. Um, it's very easy to sort of check whether something has a pole. You just look at whether it has a pole or not, right? Like there's sort of one direction of things to check. Whereas for surfaces, you end up with these issues like blowups. Right. So maybe another kind of way to say what happens here is every subscheme of a smooth curve is locally principal. You can never run into this problem of having a subscheme that isn't even locally cut out by one equation. On a curve, that always happens. On a smooth curve, singular curve, that won't necessarily be the case. So on the other hand, once you go up one dimension, there are tons and tons of birational maps between the nicest varieties imaginable, which aren't isomorphisms. And the kind of fundamental problem is that I can define this thing called a blowup. So I can look at, let's just first do the kind of easy concrete example of this. So I'm looking at A2 that has coordinates AB. I'm looking at P1 that has coordinates XY, which are only defined up to multiplication by a scalar. And this is going to be the vanishing set of AY minus BX. Right? So what this says is that AB is a multiple of XY. So this says AB lies on the line. But if AB is 0, this is no restriction at all. Right? So this obviously has a map from B to P1, which is forget the AB. This is a nice smooth map, and its fiber is always an A1. It's the line that comes from the P1. So this is the tautological bundle of P1. If I wrote this in algebraic terms, it's the total space of the line bundle O minus. All right, and I should say, right, what are X and Y in these terms? They're the functions that come from, there's a homomorphism from the line bundle O of -1 to the one called O, which is multiplication by X or multiplication by Y. And that's these line bundles. Okay, great. Everything all right? Oh, that's interesting. Huh. Did you try turning it off? Oh, that's really interesting, but it is showing this part of the board.
These two.
Huh. I see. Well, that's good. Don't think so. I don't think this controls the camera, right? Okay. Yeah, doesn't change anything. I don't. All right, I don't know what to tell you. Okay. I mean, I can also just use these two boards. Would be okay. Like, it'll be slightly silly, but it won't be the first time that that has happened. Um, all right. So, if I invert A or B, then I'm saying that one of the coordinates of A or B has to be non-zero. And so there's only one line that it lies on. So if I invert either one of these guys, this gives me an isomorphism. So if I take B and I subtract the vanishing set of A, that's isomorphic to A2 minus the vanishing set of A. All right, and similarly B. So what this is telling me is that this is actually a birational map. There's an open subset of B, which is isomorphic to an open subset of A2. Which is, subtracting the vanishing set of A and subtracting the vanishing set of A and B, subtracting the vanishing set of A. Okay, now one interesting thing to note here is here I'm pulling out a point, so I'm getting a non-affine subset of this affine scheme. Here, what I'm pulling out is the zero section of the line bundle. So the map of this guy into the total space, into B, this is an affine map, but B is not an affine scheme. So I'm sort of fixing the issue of this not being an affine scheme by making it giving it an affine inclusion into something that's not affine. But of course, this is very, very much not an isomorphism because the fiber over the point where A and B are 0 is all of P1. So I see that having 2 dimensions kind of gives me more room for something bad to happen. Mhm. Well, the kind of easiest thing to do is to compute the map to its affinization and show that that map isn't an isomorphism, right? So in this case, how would I prove that this isn't an affine scheme? Well, we proved at some point way back when that the global functions on this guy are the polynomials in 2 variables, right? So when I affinize this scheme, that gives me the inclusion into A2. Well, this is not an isomorphism, and it would be an isomorphism if I'd started with an affine scheme. Um, by affinization, I mean the universal affine scheme, the terminal scheme, the terminal affine scheme amongst all affine schemes with maps of this guy into them, which is the same as just take global functions and take spec of them, right? But the point is, if I had, I look at a map of this guy into an affine scheme, it has to factor through spec of the global functions, right? Any map into an affine scheme is induced by a map from functions on that affine scheme into global functions on your scheme, whether your scheme is affine or not. So that tells me any map of this guy into an affine scheme factors through the inclusion into A2. But the identity doesn't factor through the inclusion into A2. So I've got no hope there. Right? An affine scheme will be spec of its global functions. So if you want to prove that something is an affine scheme, you're not, you don't have to worry like, oh, is there some strange affine scheme I never thought about that this guy is isomorphic to? Because you know it has to be spec of the global functions. There also is a relative version of this where I can take one scheme mapping into another and find the terminal scheme, which is affine over this guy that this guy maps into. Right. And in that case, I would find, oh, this, I already know that this inclusion is affine. But it's because I'm using that relative part. All right. This notion, this is called a blow up. There's this old joke that you shouldn't discuss algebraic geometry at the airport because you might say you're going to blow up a family and then go back later to check if it's flat. So this sort of vastly generalizes. This is kind of one special case, and this is kind of the example you should keep in mind about how things might go wrong. In particular, you can imagine how I might increase this to n and this to n minus 1. And I would get the same story. I would have an isomorphism almost everywhere, but over this one point, I would get a copy of Pn minus 1. So in general, the blow up y sub scheme x and y is the go to sleep on me. Universal Y scheme. So I'm going to have a commutative diagram here. X mapping into Y, have the blow up at X of Y mapping in here. And then, well, I'm going to have a fiber product, which is the fibers over X in this blow up. This is going to have a particular form. Such that E of X, so this blow up Y, such that E of X including into this blow up. So whenever I have a map going down to Y, I can look at the fiber product and I can look at this inclusion. And this is going to be a subscheme, is an effective Cartier divisor. So what a blow up does is it takes a subscheme and it blows it up. It sort of inflates it to be a Cartier divisor, in particular to be codimension 1. And the sort of change in the scheme is whatever price you have to pay to make that happen. It's the fiber product. I mean, it's defined by universal property in Y schemes. So like it's the universal thing, it's term, initial, that has a map to Y, such that when I take the fiber product with X, the thing I get is an effective Cartier divisor. So that means it's locally principal. Over Y. So I take this guy, which maybe is a single point here, for example, and I blow it up to be a Cartier divisor. So in general, if I have a smooth thing and I'm taking a single point, it's always going to look like this. What I'm going to get is a projective space. And the way you can think about the projective space is it's the lines through that point in the tangent space. So if Y is, oh, sorry, yes. Yeah, no, it's so if I smooth X is a point, then E of X is equal to, this guy has dimension n, then this EX is always a copy of Pn minus 1. And it's really the projectivization of the Zariski tangent space at X of Y. Oh, sorry, yes, it should be closed, yes. So to do this in general, let me just tell you the version where Y is affine, and then you can figure out the relative version for yourself. Y is affine, so it's spec of A. Then what I'm looking for is some interesting A scheme. And it turns out you can do this projectively, so it's proj of something. So X is going to be the vanishing set of some ideal. And I'll note here, I said sub-scheme, not some subset. It's gonna matter, right? being an effective Cartier divisor is a property of a subscheme, not a subset. All right, then this blow up at x of y is Raj of a plus I plus I squared plus dot dot dot. So this is my graded ring. Its degree 0 part is A. That's the natural way to get something that's an A scheme. Its degree 1 part is I. So what am I doing? I'm forcing there to be a line bundle whose sections cut out an effective Cartier divisor that sits above X. Right? By construction, the elements of O of 1 will cut out effective Cartier divisors. Yeah. Yeah, I mean, for a general Y, I would take a relative approach, right? Which just means take your scheme, cover it with affines, do this construction on each of the affines, and then glue them together. Okay. Relative proj is just a fancy way of saying, like, oh, there's a consistent way to do that that doesn't change at all depending on how you cut things up into open sets. One fun game you can play is with curves, which we understand very well. Well, smooth curves have no subschemes that aren't locally principal. So if I go to a smooth curve and I try to do this blow up, I'll just get the same thing back again. But if I take a singular curve and I do this blow up, I might actually get something interesting. So for example, if I take x times y equals 0, then the reduced scheme structure on the point is not principal. There are other subschemes you can write down. I think I've got this right. I said this in my notes. Now I'm worried that this is wrong, but I think I should get the blow up here and get this guy. Yeah, that's exactly. Okay. I was just like, wait a second. Yeah, anyways, we'll worry about it some other time. And this is certainly what you should get. And, similarly, if you take this cusp, that's squared minus y cubed. I drew x squared, x cubed minus y squared. I do this and I just get a copy of A1. So if you do this to singular curves, you're constructing the normalization. Whereas if you do this to a surface, you can really change the underlying thing, and you can just keep doing this more and more times. So one kind of interesting thing is this tells you there's an infinite class of surfaces which are all birational to each other, because I can just take E2 and I can start blowing it up. Oh, sorry, yes. Good point. E2. Blow up at K points. So these are surfaces that are all birational to each other, and they're all different. I don't know that we really have the kind of technology to check that they're all different, but one reason that they're all different is they all have different size Picard groups. So the Picard group of P2 is 1 copy of Z. If I blow up at K points, I'll get K plus 1 copies of Z. Basically, every time I blow up, if I blow up at a point, I add in this new Pn, and the line bundle that I use to construct the blow up gives me a new generator of the Picard group. Now you can see in these cases, it doesn't have to be non-trivial, but in the case of blowing up P2 at a point, I'm just going to keep adding a new copy of Z to the Picard group. Yeah. Well, I just mean any subset of K points. Like choose K points, you can blow up look at the reduced scheme structure on those K points, you can do that blow. All right. Feel like I'm hearing questions on no, or is that okay? Anyways, I'm hearing some kind of notification noise, but that's so if you have yeah, it might be the disk notifications. I see. Okay. Great. All right. All that stuff. Okay. Yeah. Um, all right. So how do we find surfaces in the wild? How do we start to actually sort of think about this stuff? Um, hmm? Oh, yes. Sorry. Yeah, I will. Just, have it. I'll message IT about this. Yeah, pretty much. Okay, so how do we find surfaces? Well, there's one kind of obvious way to find surfaces, which is to look at P3 and to look at hypersurfaces in there, to look at the vanishing set of a polynomial. And I should think of this polynomial as being in 4 variables. One of the things that's always tough about projective space is keeping in mind when you have to do more variables. All right, so the kind of key invariant here is the degree of this polynomial. And of course, I want it to be homogeneous to give me something in projective space. This guy has some degree. Degree 0, I'm not going to worry about. That doesn't give me anything. D equals 1, well, I just get copies of P2. Cut out by single line. It's helpful to think about what's going on in terms of linear algebra. In this case, I would have K4, and I would be taking a linear thing. So I would be cutting out a 3-dimensional subspace in here, whose projectivization is P2. And one of the things we're going to be thinking about for whatever time we have is about lines in these guys. And one thing I certainly had to remind myself a few times while preparing class is, right, everything is 1 dimension up. So a 2-dimensional subspace gives me a line, which is a subscheme isomorphic to P1, whereas this guy gives me a plane. And just to continue the discussion, if I choose a 1-dimensional subspace, of course, that gives me a point in projective space. So it's just sort of important. We're going to be talking about lines inside other subschemes in P3, and it's helpful to keep in mind that actually means a 2-dimensional subspace. All right, that was not that interesting. What about D equals 2? So these are often called quadrics. For whatever reason, people just decided quadratic was too long. And if we think about these in terms of linear algebra, what are we looking at? We're looking at a bilinear form on, I should say, a quadratic form on my 4-dimensional space. Oh, all right, so in general, this could get a little bit complicated, but let's think about in the algebraic closure. So if my field is algebraically closed, then I'm sort of going to get a kind of nice picture here, which is all quadratic forms are the same. I can choose any one I want. And often it will be helpful to choose ones which are not very sort of symmetric, right? When you think quadratic form, you probably think, x squared plus y squared plus z squared plus w squared. And there's some purposes for which that's a very nice quadratic form to look at. And there's some purposes for which it's a very bad one. Okay. So one nice one to look at is I can think of K4 as 2 by 2 matrices over K. And there's a very nice bilinear form on 2 by 2 matrices, which is the determinant. That's a quadratic form. Now, it's incredibly non-positive definite, right? If you're used to thinking over R, that looks incredibly different from x squared plus y squared plus z squared plus w squared. But over the complex numbers, they're actually the same. And when I think about it this way, the structure actually gets very nice. What do the 2 by 2 matrices with vanishing determinant look like? So non-zero, since I'm looking at projective space, 2 by 2 matrices with determinant equals 0. Well, since they're non-zero, I've ruled out rank 0. And since their determinant equals 0, I've ruled out rank 2. So they have to be rank 1. So in that case, I can write them as the product the wrong way. Well, let me not use those, of a column vector and a row vector. I get S U T U V E. So what I see here is I'm choosing 2 lines in 2 by 2 space. And so what I get is that my vanishing set of the determinant is isomorphic to P1 times P1. And if I had taken a non-algebraically closed field here, well, remember we already saw this issue about P1. There kind of isn't a unique P1 over non-algebraically closed fields. There are also other conic sections. And so similarly here, you'll always get something that when you base change the algebraic closure, you get P1 times P1, but there can be various weird interactions with the Galois group. And maybe I'll mention here, if you know this fact that SU2 times SU2 is a double cover of SO4, this is another manifestation of that fact. So if I instead, right, if I think about this quadratic form as coming from a symmetric bilinear form, there's an SO3 that preserves that. SU2 times SU2 will act on this P1 times P1 in the usual way. Yeah, I think probably this is fine over bases that aren't a field, but I haven't thought about it super carefully. Certainly you'd have to be kind of careful about this. sort of going to the algebraic closure and picking one specific form of it, but I think you actually can make it work and always find the ruling. There's sort of a lot of these statements where it's kind of a little easier to see why they work if you think over an algebraically closed field or something, but actually quite a few of these don't depend very much on that when you get right down to it. All right, so I think it's clear we're not going to have time to finish this discussion today, but what about d equals 2? So this gives me cubic surfaces. All right, and there's a very famous theorem. I'm going to make sure I get one of these statements right. Oh yeah, d equals 3, sorry. Yeah. So how do I think about these? So one nice thing about thinking about varieties as zeros of these polynomials is I know how to think about the set of all of them at once, because I just look at the polynomials up to scalar multiplication, and that parametrizes my various possibilities. So for example, for d equals 2, I have to think about how many degree 2 monomials in this guy there are. And if I'm remembering right, I get P9, which parametrizes these guys. With the coordinates on the P9 being the coefficients of the polynomial. Right. So similarly here, I end up with a P19. So I have my polynomial f. I can write this as c x cubed times x cubed plus c x squared y times x squared y, dot, 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 dot. And there are 20 of these coefficients, so I get a P19 parametrizing these guys. And thinking about the dimensions of these spaces is kind of useful for thinking about what kind of structures they'll have and how those structures will behave. So inside here, there's a subspace, which is my cubic x equals v of f is singular. So one of the arguments, Vacchia leaves this as an exercise, but well, we can talk about it later if you want, is that this is actually an irreducible subscheme. I believe it's a divisor. Hopefully I'm remembering that right. And one way to think about this is you can sort of write down some horrible polynomial in the coefficients, which is going to tell you whether your cubic is singular. But you can also think about the set of pairs x, e is a singular point of x. So one of the places where scheme theory becomes very useful, even if you just want to do classical algebraic geometry, is to sort of think about spaces like this and think about questions like, is this guy reduced? Right? That can end up being pretty important. All right. So these smooth guys, unlike this picture, they aren't kind of quite all the same. We'll see in a little while, probably next time actually, how they are all similar but not literally the same. Um, but they do have something important in common. Theorem. Uh, if X is smooth, and X contains 27 lines, and is isomorphic, hopefully this is still visible, to P2 blown up at 6 points. Now I should emphasize here that there are surfaces which are not P2 blown up at a bunch of points. There are in fact many of them. Sort of, you should all generic varieties of any degree will not be birational to Pn. Sort of most of the time, you will not be birational to Pn. And we see this with curves, right? Only genus 0 curves are birational to P1. Anything else has a different function field. So somehow, you shouldn't use the word genus for surfaces because they're much more complicated invariants. But somehow this is kind of like we've only seen genus 0 surfaces. And there are many more out there which come from kind of more complicated things. Yes. Yeah. Yeah. This means that there are 27. Oh, okay. So yeah, in here, a line is the projectivization of a two-dimensional subspace. So I mean that there are 27 such subschemes which lie inside X. Which, sort of Vakil has this quote that's if you go up to an algebraic geometer while they're sleeping and whisper the number 27 in their ear, they'll complete the phrase with lines in a cubic surface. So there are sort of lots of numerical results like this from classical algebraic geometry, and this is somehow the most famous of them, in part because it's sort of the nicest. Often you'll get these statements that are more like, well, if you count these with multiplicity, right? Bezout's theorem, for example, um, tells you how many intersections there are between two curves in P2, but it tells you have to count with multiplicity. I didn't say 27 lines with multiplicity. They all are sort of forced to have multiplicity once. So they're genuinely 27. And this result about it being P2 blown up at 6 points, right? It has this problem of we haven't discussed enough about different surfaces for you to understand how surprising that is. That it's not some completely random guy up to birational things. It's birational to P2. Okay. No. I mean, so let's kind of start setting up the proof. We obviously won't have time to talk about it in much detail. So the key thing you want to do in the proof is you want to look at the scheme defined by XL. So X, a cubic surface, not necessarily smooth. L a line, and X contains L. All right, so these cubic surfaces, they're parametrized by P19. The lines, they're parametrized. So Vakil writes this as G13. I find this kind of horrible. Any normal human would think of this as the Grassmannian of two planes in four space. I genuinely got confused because I'd forgotten that Vakil indexes his Grassmannians off by one. Yeah, yeah, yeah. Vakil uses bold G as well. All right, so the map here, so in the cubic case, this map is finite, right? What we're going to find is that over the smooth points, it's finite with degree 27. So if you looked at like the function field of this guy and the function field of this guy, this would be a weird degree 27 extension of this guy. And if you go through all the numerics, the difference in dimension, so this has dimension of how much is the dimension of this guy more than the dimension of this guy is 3 minus d. So if I take, which is telling me if I take sort of a generic thing here, what dimensional space of lines do I expect it to include? So if I have something degree 1, that's a P2, it contains a two-dimensional space of lines. Coming from the projectivization of, and if I take D equals, so that was D equals 1. If I take D equals 2, I get a one-dimensional space of lines. I have P1 times P1, and I have two families of lines. So if I looked at the generic fiber here, I would get P1 union P1, corresponding to the two families. This is sort of a famous fact about quadric surfaces, that they have these two rulings. So D equals 3 is exactly when these guys have the same dimension, and I expect there to be finitely many lines. So this is what's called an incidence variety. You know, sort of one of the first kind of games that people played and you know, way back over 100 years ago was kind of, you know, figuring out when these incidence varieties would have the right dimension that you would expect finitely many solutions, and then trying to figure out how many solutions there were. All right. Yeah, well, that's all we have time for, so maybe I'll stop here. This guy has the same dimensions as this guy. So what we want to show is that over the smooth locus, this map always has finite 27 elements in its fiber. So there's kind of an abstract argument for why that number is always the same, and then you do one calculation and see that there's one cubic surface that has 27 lines. All right. But I guess we'll have to save that for next time.